forgetting about what happened the last time I was mic'd and recorded. All right, so this talk is on Hodge theory and combinatorics, and it's about solving specific problems in combinatorics using techniques from Hodge theory. And I'm going to start with explaining a particular problem that I would like to solve. And this one involves the characteristic polynomial of a subspace. So I'm going to let K be some field. I'm going to let V inside an n+1 dimensional vector space. I'm going to let V be an r+1 dimensional linear subspace. And what I'm interested in doing is expressing V intersect K star to the n+1 in terms of coordinate subspaces. Here, K star to the n+1 is the algebraic torus inside of Kn+1. It's a set of all points, none of whose coordinates are 0. And I'm going to do an inclusion-exclusion type expression. And I want to express it in terms of coordinate flats. So these are sets of the form V intersect Li, where Li is the set of all points in my subspace where the coordinates corresponding to elements of I are 0. So here, I is a subset of 0 through n. So I'm labeling the coordinates in Kn+1, 0 through n. So it's more clear when I give an example. So if V is a generic subspace, in other words, it intersects every coordinate flat in the expected dimension, then we have the following. We start with V itself, which I'm going to write in the following form. Then we subtract the set of all points where one coordinate is 0. But then we've subtracted too much because we've subtracted all the points where two coordinates are 0. So we add them back in. And so on by inclusion, exclusion. And if you are a fancy person or a nerd, you might say that this is a motivic expression. All right, and for more general subspaces, we have to be slightly more careful because the V's intersect Li's may not specify unique subspaces. So I'm going to define a set I inside 0 through n is a flat if, for any set strictly containing I, the intersection is smaller. And then the rank of a flat is the codimension of the intersection inside V. And then, if you believe in this motivic expression that I wrote down, you can do it in general, and you get some unique expression of the following form. So we sum over the flats I, including the empty flat, and we're looking at V intersect Li, weighted by some integers nu sub I. And it's a fact that the nu sub i's alternate in sign depending on rank. And once we have that, we can get a unique expression. And what I'm going to do is I'm going to condense this expression into a polynomial called the characteristic polynomial. So the characteristic polynomial of this subspace it's a polynomial in a variable q, and it's defined to be the following. So we let I run over all the possible ranks of flats. Then we sum over the flats of rank I. And then we had a variable q, which would be the dimension of the flat. And I'm going to call the coefficients of the characteristic polynomial mu sub lower i's. And if you're a nerd, again, you can call this a motivic valuation. So it's given by a motivic valuation taking the class V intersect Li to Q to its dimension. So in the case of our generic subspace, what we get is the following for the characteristic polynomial. So just an alternating sum of binomial coefficients. Is there a dial to adjust the pickup on the mic? It just seems awfully sensitive. See, this is what I said about trusting me with a mic. Yeah, it just seems a little sensitive. Is there just a way of turning it down a slight bit? Otherwise, I'm just watching my breathing. I'm like, can I breathe now? Can I breathe now? Like, I'll turn blue and pass out. All right, all good? OK. So now let me tell you about what used to be the Rota, Hare, and Welsh conjecture in the realizable case, and is now a theorem with Jun He. And H/K, we did this in 2011. Notice the lowercase k, which is that the characteristic polynomial is log concave and internally zero free. Hence unimodal. And I'll tell you what these words mean in a second. So what log concave means is that the sequence of coefficients, their logs form a concave sequence. So a polynomial with coefficients mu0 through mu r plus 1 is said to be log concave if it satisfies the following inequalities. So if for all I and here internally zero free means the only zeros in the sequence occur at the beginning and the end. And when you combine internally zero free with log concave, you get unimodality, which says in absolute value, the coefficients increase, then they decrease. Not necessarily strictly so. So here unimodal means the following. And we don't know where the peak is. We don't know that the mu i's are necessarily symmetric. In fact, they aren't. But we know that in a non-strict sense, the peak occurs, well, that they increase, maybe stay the same for a while, and then they decrease. And the original motivation of this was a conjecture about chromatic polynomials of graphs. So if gamma is a loop-free graph, we can define the chromatic function to be the number of proper colorings with Q colors. And here, proper colorings mean I assign one of Q colors to every vertex with the condition that no two vertices of the same color are joined by an edge. And it's a fun thing to prove that this function is a polynomial, where its degree is equal to the number of vertices, and it's got alternating coefficients. And it was a conjecture that Reed made in 1968, and Jun He proved in 2010 that the chromatic polynomial is unimodal. And this is a very interesting conjecture. Like, I've read about it in graph theory, and Tut said, like, the chromatic polynomial was originally developed to help prove the four-color theorem, which it didn't do. And I read, I think in Tut's graph theory as I know it, that he said something like the chromatic polynomial, having failed to prove the four-color theorem, offers us this for our bafflement. All right, and it turns out that the chromatic polynomial coincides up to a factor of Q with the characteristic polynomial of its cycle space. All right, everyone happy? Okay, so now let me talk about an abstraction of the Roda-Heron-Welsh conjecture. So that was a theorem, as I stated, about subspaces. I want to abstract subspaces to matroids. So what matroids are an oracle that tells you the rank of the subspace, or the rank of the corresponding set, had the vector space existed. So the matroid is a rank function from subsets of the set of integers from 0 to n to the integers, satisfying the following properties. The rank of a set lies between 0 and the set's cardinality. Remember, rho I for a vector space was codimension of the corresponding coordinate subspace. So here I impose cardinality of I conditions, and I expect it to cut down the dimension by, at most, cardinality of I. Second condition is when I impose more conditions, when I force more coordinates to vanish, then the codimension gets bigger, or is not increasing. The third condition is complicated. And the fourth condition is that if I set all the coordinates equal to 0, I end up with something of codimension r plus 1. All right, and now the mysterious third condition is just subadditivity of codimension of intersection of subspaces when you write this out. And there are about 5 different definitions of matroids. They all are of the form, here are several obvious things, and here's something totally inscrutable. But this inscrutable thing is just subadditivity of codimension. OK, and now I'm going to state the full-blown Rota-Heron-Welsh conjecture. So I can define the characteristic polynomial purely combinatorially using a technique called Mobius inversion. So I can talk about the characteristic polynomial of a matroid, and the conjecture is that it's log concave and internally zero free. All right, and up to checking some details, this is no longer a conjecture. So Kareem, June, and I are in the process of writing up a proof using some ideas from Hodge theory. Mostly today I'm going to talk about our proof in the realizable case. And then I'll explain how to establish it combinatorially. But before I do that, before I tell you something really exciting, I'm going to change the subject. So I'm going to talk to you about a different problem. And then I will find common ground between this different problem and the Rota-Heron-Welsh conjecture. And this different problem is the lower bound theorem in polyhedral combinatorics. So I'm going to let P be a full-dimensional convex polytope. And for convenience, I'm going to make it simplicial, meaning every face is a simplex. Every proper face is a simplex. And I can look at the face numbers. So f sub k is the number of k-dimensional faces. And we can ask, what are the possible numbers of k-dimensional faces for all k? So in this, McMullen gave a conjectural description based on a lot of numerical evidence. And his conjectural description was proven by Balera and Lee and Richard Stanley. And we're going to only talk about the necessity part of only one part of his description. So I need to work with a different encoding of the face numbers. So I'm going to define the h numbers. So I'm going to take a generating function for the face numbers. I'm going to do a linear change of variables to produce the h numbers. And the Dane-Somerville relations tell you that the h numbers form a symmetric sequence. And that isn't very deep. It's messing around with Euler characteristics. And then the lower bound theorem, as conjectured by McMullen and proven by Stanley, says that the h numbers form a unimodal sequence. And here they're symmetric, so the peak is halfway in the sequence. And notice in this sense, this unimodality is different from the unimodality that we're interested in the Rota-Heron-Welsh case, because the numbers are symmetric here, so we know where the peak is. And we'll actually see this through the methods of proof. And let me rephrase the McMullen's conjecture in terms of commutative algebra. So I need to tell you really quickly about Stanley-Reisner rings. So I'm going to let delta be the boundary of our polytope considered as a simplicial complex. I'm going to let V1 through Vn be the vertices of our polytope. And I'm going to introduce variables corresponding to these vertices. I'm going to call those variables x1 through xn. And there's a special ideal inside the polynomial ring on the xi's. And it's defined as follows. So for some subset of the vertices, I'm going to let x to the s be the product of the corresponding variables. Then the ideal, the non-face ideal, corresponds to, they're the monomials, it's generated by the monomials corresponding to the non-faces of the boundary of P. Actually, it's generated by. There we go. Okay, and the Stanley-Reisner ring is the quotient of this polynomial ring by the non-face ideal. So that means the square-free monomials in the Stanley-Reisner ring correspond to faces of the polytope. And because the non-face ideal is a graded ideal, the Stanley-Reisner ring is a graded ring. And now I'm going to pick generic degree 1 elements. Lambda 1 through lambda d. So the number is of generic degree 1 elements I pick is equal to the dimension of my polytope. Then it turns out that the dimension of the quotient of the Stanley-Reisner ring by the ideal generated by these degree 1 elements are the H numbers. So the quotient is a graded ideal. I'm looking at the dimension of the I-graded piece. So maybe I'll write it like that. Then the lower bounds theorem, the unimodality statement, becomes a theorem about the existence of a Lefschetz element. So here, a weak Lefschetz element is a degree 1 element of the Stanley-Reisner ring such that multiplication by it is injective on this quotient in up to half the degree. Okay, so if we can find such an element, then we derive the unimodality statement for the H numbers. And the existence of this element comes from identifying this Stanley-Reisner quotient with the cohomology of an algebraic variety. So So Stanley's proof there exists an algebraic variety. It turns out to be a toric variety. It's a projective algebraic variety such that the HIs are the dimension of the even cohomology. And then the hard Lefschetz theorem on the variety X gives a Lefschetz element. So this result relies on hard algebraic geometry, but McMullen was able to give a combinatorial proof in the simplicial case, which was extended to the non-simplicial case by Kali-Carew. And McMullen's proof uses an alternative presentation of the Stanley-Reasoner ring. And what he does is he uses induction on the complexity of the polytope. So he starts with a simplex. And it's known, hard Lefschetz is known to hold for the simplex. And he reduces any polytope to the simplex by basically pulling in a wall from infinity, and letting it sweep out the polytope. So what you're doing is you're imagining you're imposing an additional condition by intersecting your polytope with a half space. You keep moving the half space in until you have a simplex, then you move it back out and show that your polytope changes in predictable ways by flip moves, and that hard Lefschetz is preserved by those flip moves. And turns out there's actually several different presentations for the cohomology of this toric variety, or of the Stanley-Reasoner ring. So there's the Stanley-Reasoner ring, which you should really think of as Chow homology as generated by divisors. Then there's a Minkowski weight ring, which is what McMullen used, which is cohomology. And then there's the cone-wise polynomial ring by Carew, which is a quotient of equivariant cohomology. And I should mention that these synthetic Hodge theory arguments have found other places in combinatorics. So there's recent work by Ben Elias and Jordy Williamson proving the hard Lefschetz theorem to prove the positivity of the Kazhdan-Lustig polynomials in the context of Coxeter systems. In this case, if your Coxeter system corresponds to a Weil group, then you're studying the intersection cohomology of a Schubert variety. In the more general case, you need some kind of combinatorial stand-in for a Schubert variety. All right, so now let me tell you about the hard algebraic geometry that goes into these proofs. So I'm going to discuss two theorems, the hard Lefschetz theorem, which plays a role in our proof of the Rota-Heron-Welsh conjecture. I'm sorry, the hard Lefschetz theorem, which plays a role in the proof of McMullen's conjecture, and the Hodge index theorem, which plays a role in our proof of Rota-Heron-Welsh. And then I'm going to explain how they're implied by an even deeper theorem, the Hodge-Riemann-Minkowski relations. All right, everyone happy-ish? No one looks happy. All right. All right, so we're going to let X be a smooth, projective, d-dimensional algebraic variety. Then its cohomology is a graded ring in dimensions 0 through 2D. And it has a Hodge decomposition. Oh, I should mention also that its top dimensional piece is one-dimensional. And let's use C coefficients here. Then we have a Hodge decomposition into the PQ bits. Then if H is a generic hyperplane in Pn, intersecting with H gives you a Lefschetz element. So we're going to let H be a generic hyperplane in Pn, then we can view intersecting with H as an element of H2. So I guess we'll view H intersect X as a codimension 2 cycle. Then the Hard-Lefschetz theorem, which is due to Hodge, tells us the following. So we're going to let L be the map on cohomology given by intersecting with H. Or we could say in cohomology by multiplying with H. Then we get the following isomorphism. Okay, and we know these two cohomology groups have the same dimension by Poincare duality, but here we get an explicit isomorphism by multiplying with the Lefschetz class. And this implies that multiplying by L once is an injection. And that implies the unimodality of the H2i's, or implies the unimodality of the dimensions of the cohomology groups. No. It actually turns out not to be smooth. In the simplicial case, it has very mild orbifold singularities. That's enough for a proof of Hard-Lefschetz to go through. In the non-simplicial case, then you have to use intersection cohomology, where Hard-Lefschetz is also defined, or also holds, but the definition of intersection cohomology is really hard, or really difficult. All right, so now this Hard-Lefschetz actually lets us break up the cohomology in nice ways. So we get a Lefschetz decomposition of the cohomology. So I can define the primitive cohomology to be the kernel of multiplication by the Lefschetz operator, where I apply it one more time than is used in Hard-Lefschetz. And let me show you how I think of, or then you get a decomposition as follows, and I'll tell you how I think about it in a sec. Okay, we're just going to look at the even cohomology. So we're going to look at stuff in degree 0, 2, 4, 2D, 2D minus 2, and 2D minus 4. Now, let's say I start with some cohomology class in degree 0. I start applying L to it. I know it's going to survive all the way to the top dimension. Now, there's some cohomology in degree 2 not coming from dimension 0. When I start applying L to it, I know it'll survive to codimension 2. Then there's stuff in degree 4 not coming from the smaller degrees, and I know it survives to 2D minus 4. So I get this sort of decomposition of cohomology. And here, this direct sum just comes from reading down this column. All right, and I'm going to come back to this, so don't forget it, but I want to tell you about the Hodge index theorem. So the Hodge index theorem is a theorem about surfaces. So algebraic surfaces, which are 4 real dimensions. And I'm going to consider the second cohomology equipped with the intersection product. And the content of the Hodge index theorem is that the intersection product restricted to H11 is non-degenerate with a single positive eigenvalue. And this immediately implies the Hodge inequality. And you'll notice it'll look a lot like a log concavity statement. So we're going to let alpha and beta in H11 be ample classes. So that means those are classes whose some power of which comes from pulling back a hyperplane. Then we have the following inequality of intersection numbers. Then you have the following inequality. And notice it also looks like Cauchy-Schwarz with the inequality going the wrong way. And the proof of this is that the intersection product is semi-definite on the span of alpha and beta by the Hodge index theorem. You write down the intersection product as a matrix on this vector space, and then you notice that the determinant of this matrix must be negative, and you write down what that means, and you get exactly this inequality. And we should also notice that this theorem behaves well with respect to continuity. If we take a limit of ample classes, it'll be true for the limit, and we know the limit of ample classes are Neff classes. Don't worry if you don't know what that means. It just means they can, by a theorem of Kleiman, it means that they can be approximated by ample classes. OK, so now I'm going to finally get to the Hodge-Riemann bilinear relations. And this is a much more complicated theorem that implies both the Hodge index theorem and Hard-Lefschetz. So I guess I'll call it Hodge-Riemann-Minkowski bilinear relations, because there's something analogous in polyhedral geometry to it. So let alpha be an ample class, and we're going to let P star be the primitive cohomology with respect to alpha. Then I'm going to define a pairing QPQ on the primitive cohomology of degree PQ. this is a big mess, so give me a second to write this. That this pairing is positive definite. All right, so let's stare at the formula for the pairing. So let's not worry about the i's and the signs. Let's just worry about this term. And here, this expression means the degree of this cohomology class. So I have classes beta and beta and gamma. I cup them together, and then I take a big enough power of alpha to knock it into the top degree. This theorem says this pairing is positive definite on the primitive cohomology, and we've got a primitive decomposition. So this says that a certain pairing is non-degenerate on all pieces of the decomposition. And it turns out, under this pairing, the Lefschetz decomposition is orthogonal. And therefore, this says that this class beta can't be eaten by this power of alpha. So that's where it's stronger than hard Lefschetz. Is everyone happy with that? Does everyone buy that? OK, and yeah, of course, this is really ugly and complicated. So let's just restrict to classes of PP type. So there, we just have an alternating sign. All right. As a corollary, we immediately get the Hodge index theorem. And let me give you the proof. H11 decomposes into L times H00 primitive bit, direct sum H11 primitive. By looking at the definition of primitive cohomology, we see that this is an orthogonal pairing with respect to Q. And Q is positive definite on this bit and negative definite on this bit. So therefore, we get the Hodge index theorem. And moreover, you should really think about this theorem as the generalization of the Hodge index theorem to higher dimensions. And from this theorem, we can get the Khovansky-Tessier inequality. Which is a generalization of the Hodge inequality. So, and it says for alpha and beta Neff, we have the following inequality. Guess it's I between. And now this really looks like log concavity. All right, so now let me give you the proof of log concavity in the realizable case. So the first step is we use the reduced characteristic polynomial, which is just the characteristic polynomial divided by q minus 1. Turns out 1 is a root of this polynomial, and I'm going to write this guy as a polynomial. I'm going to call its coefficients mu upper I. And these mu upper i's have a combinatorial expression. And now I'm going to define a Stanley-Reisnerish ring associated to my vector subspace. So it's a Stanley-Reisnerish ring of a matroid. So I'm going to have indeterminates indexed by proper flats. And I'm going to define an ideal as follows. So I sub m is the ideal generated by the following relations. So there are linear relations for any pair I and j among the ground set of the matroid. We have the following relation. We look at all the flats containing I, and I subtract all the flats containing the ground element j. And then I have an incomparability relation which should be thought of as generalizing the non-face relation, or as analogous to the non-face relation. And then I'm going to let my Stanley-Reisnerish ring be the quotient of the polynomial ring generated by the x sub f's by the ideal I. So if we just had relation 2, then we're taking this Stanley-Reisner ring of the order complex of the lattice of flats of the matroid. But here we're quotienting by this linear ideal, and the linear ideal looks too big, like from the point of view of Stanley-Reisner theory. But somehow that makes it work. And this ring has nice properties. So turns out there is a degree map on the r-dimensional piece of this ring. Remember that our matroid was rank r plus 1. And it's an isomorphism, and it takes the value 1 on an ascending chain of flats. But on a complete ascending chain of flats, meaning I take flats of rank 1 through r. And now there are two very important degree 1 elements of our ring. So I'm going to pick my favorite element of the ground set. And I'm going to define a class alpha to be the sum of all flats containing I. And I'm going to define a class beta to be the sum of all flats not containing I. And a lemma that we prove by tropical intersection theory, but you can just prove by doing intersection numbers in our ring, is that the degree of products of alpha and beta are the coefficients of the reduced characteristic polynomial. And the way we get log concavity is through the following theorem, at least in the realizable case. And let's just make it realizable over C, so we can use the full Hodge theory apparatus. If M is realizable over C, there is an algebraic variety V tilde whose even cohomology is our ring. Moreover, alpha and beta correspond to Neff classes on V tilde. And the Hodge-Riemann-Minkowski relations hold for suitably perturbed alpha and beta. So you get the Hodge-Riemann relation, so you get the Khovansky-Tessier inequality, and that gives inequalities between the intersection numbers of alpha and beta, which, by our lemma, give the log concavity inequalities for the coefficients of the reduced characteristic polynomial. And we can actually shortcut this. If it's not realizable over C, we can get the Khovansky-Tessier inequality through other means by implying by using Kleiman transversality. Anyway, but I want to talk about going through the Hodge-Riemann-Minkowski relations. All right, and our construction of the space V tilde is natural. So to produce V tilde, we have to blow up the projectivization of our linear subspace. So recall that we had V inside Cn plus 1. So that means its projectivization lives in n-dimensional projective space. And we've picked coordinates on this n-dimensional projective space. So we have coordinate hyperplanes, we have coordinate lines, we have coordinate points. So we start by blowing up the coordinate points, meaning the points in Pn, only one of whose coordinates is non-zero. Then I blow up the proper transform of the lines between the coordinate points. Then I blow up the proper transform of the planes containing 3 of the coordinate points, and so on. And it produces a space V tilde. And V tilde lives in a blown-up projective space. So if we apply the same operation to Pn, where we just blow up all the coordinate subspaces and then take the proper transform of V, we get V tilde. And really, you should think that V tilde resolves a Cremona transform. So really, you should think of the following happening. We have Pn tilde, which resolves the indeterminacies of the following birational map. So it's the map that takes a point in Pn to the point whose coordinates are the reciprocals. And we have projections onto the domain and on the image. And alpha is the pullback of a hyperplane class from the domain. Beta is the pullback of the hyperplane class from the image. And these guys are ample on the Pn, so they turn out their pullback ends up being Neff. And what you can do is you can perturb alpha and beta to make them ample again, apply Hodge-Riemann-Minkowski, go get the Khovansky-Tessier inequality, and take the limit back. All right. So some of you have seen this talk before, and at this point, when I usually give this talk, I ask, can this argument been made purely combinatorial in order to prove the full-blown Rota-Heron-Welsh? And every time I've suggested some proof or some technique that ultimately doesn't work, And by the end, I made jokes about how this whatever technique I was suggesting was doomed to failure. All right, well, this time is different. We have some details to check, but we're very confident that we did it. And the idea is to do these blow-ups combinatorially. So we have a Stanley-Reisner ring, or a Stanley-Reisner-ish ring, which we want to show obeys Hodge-Riemann-Minkowski. Well, we can start with ordinary projective space, which is just a polynomial ring in one variable. We know it satisfies Hodge-Riemann-Minkowski, and we do the combinatorial analog of blowing up. And that means it's a certain modification of our Stanley-Reisner ring. Not modification in the tropical sense. It's a certain related ring that has the properties of the ring before, but blown up at a smooth center. And then we have to verify that Hodge-Riemann-Minkowski is satisfied on these intermediate Stanley-Reisner rings. And we keep blowing up until we get our desired Stanley-Reisner ring. And the one way of thinking about this blow-up technique, if anyone thinks about polytopes, there's a certain beautiful polytope called the permutahedron. And really what these blow-ups correspond to is starting with a simplex and moving in faces from infinity to slice off faces of the simplex until we get the permutahedron. And this is sort of a combinatorial Stanley-Reisner-ish way of doing this. And the technology for Hodge theory, for doing this in Hodge theory is fairly well established. So there's ideas of McMullen and Carew that have been elevated to like a cornerstone of Hodge theory in the work of De Cataldo and Migliorini. And there are several different steps, and I will just briefly read them off and then show you what the last step is for your befuddlement. OK. So we need a combinatorial analog of the ample cone. And that's going to be the ample cone pulled back from some ambient torque variety. Then we have to verify that our Stanley-Reisner ring satisfies Poincare duality of the appropriate dimension. Then we need to show that if two of our rings satisfy Hodge-Riemann-Minkowski, their skew tensor product does, because we have to build things out of skew tensor products. I haven't defined that, but it's related to the fact that a face of a permutahedron is the product of two smaller permutahedra. Then we have to show that if all the skew tensor products of rank r-1 satisfy Hodge-Riemann-Minkowski, then our intermediate Stanley-Reisner ring satisfies hard-Lefschetz. And then, this isn't so hard, this is just a deformation theory, or a homotopy argument, show that if an intermediate Stanley-Reisner ring satisfies Hodge-Riemann-Minkowski for one ample class, it satisfies it for all of them. And then we need to show that our intermediate Stanley-Reisner ring satisfies Hodge-Riemann-Minkowski with respect to one ample class. And let me just... Oh, dear. Yep. Oh, yeah, sorry. So do you guys want to see it, or should I? Let me just give you this theorem for your befuddlement, because I suffered for it for like 3 weeks. So here's a fun, hard exercise in algebraic geometry. X is a smooth projective variety. H is an ample divisor. Z is some smooth subvariety. And let's suppose we know X and Z satisfy the Hodge-Riemann-Minkowski relations. Show, actually maybe I'll make this as an exercise. Show the blow-up of X at the center Z satisfies Hodge-Riemann-Minkowski with respect to H minus a tiny bit of the exceptional divisor. And I mean, because this is the obvious candidate ample class on a blow-up. And this is just prove this using just linear algebra. It's incredibly frustrating. Like, I totally recommend that as an exercise. It's a perturbation argument. It's fun and frustrating, and will be in our paper. Anyway, questions?